Um, so we mentioned earlier that one of the main application areas of Laplace transform is solving differential equations. And the reason differential equations are of interest are because it's found to model very systems well. And so certainly in circuit theory, capacitance has C dV dt, inductors L di dt. And so we see differential equations in many systems. Same thing is true in mechanical systems and acoustics. Um, so one of the popular methods, once you figure out the differential equation for a system, is the method of judicious guessing. And so that's probably the first crack that you take at solving differential equations. And so typically you guess e to the st is the solution. And then you kind of plug that in and work it out and solve for whatever coefficients make the solution work. Um, and so when you worked with, if you plug in, let's say quickly as an example to review this, if you haven't seen it for a while. So if we have a differential equation, some function g of t we don't know is going to solve the differential equation. So we just plug in for g of t e to the st. So plug that in here. Take its derivative. So the second derivative is going to get s squared e to the st. The first derivative is going to get se to the st. And so all that must equal 0 on the right side. So pull together the pieces. And now we have this must equal 0. And so clearly, if this piece equals 0, then it'll satisfy the differential equation. So from this, we just solve for the values of s that will satisfy this solution. So obviously, if s equals 0, the solution satisfied, and also if s equals minus k, the solution is satisfied. And so either of those will satisfy, both those functions individually would satisfy the solution. And so a solution that's the sum of those two, so this is the first, s equals 0. This is the second, s equals minus k, times some arbitrary constant will satisfy the differential equation. To check that, you can just plug that back into the differential equation, the whole function with those two added together, and kind of review that indeed this satisfies the differential equation, even with arbitrary constants a and b. And if you recall, the final step in solving the equation was to use initial conditions of some sort to solve for the remaining constants a and b to solve the differential equation. We could just, instead of using the art of judicious guessing, we could have just plugged in and used Laplace transform directly. So we could have taken the Laplace transform of the whole formula. And if you recall, the Laplace transform of a derivative is just to multiply by s. And so we have a factor s and a factor s squared. We took the derivative twice for the first term. And then the Laplace transform of g of t is g of s. So we could arrive at the same equation as we had above with the art of guessing by just taking the Laplace transform of the differential equation. And so for these many reasons, Laplace transform is closely coupled to engineering problems that involve differential equations, which means most engineering problems involving capacitors, inductors, and things of that sort. So before I leave that, why does the judicious guess of e to the st work so well? Well, we had mentioned a little bit earlier. It's because it's an eigenfunction. It's that special function where when you operate on it, it has the same form at the output as it did at the input. In particular, the derivative of e to the st has the same e to the st form as before, but then it's multiplied by some value s. And so s is called the eigenvalue. And e to the st is the eigenfunction. Notice that the s has no time component in it. And so the time variation is still controlled by the e to the st. And s is typically a constant, as we saw in the last example. It's a number that arises from the solution of the differential equation. And so it's just a scaling value. Let's say its value is 4, 5, or 6. It'll just scale this e to the st function by that factor. And so it can be complex in general or a real number. As we saw in the previous slide, the Laplace transform kind of gave us the same end result. Lastly, as we mentioned a bit earlier, so typically most engineering problems aren't as easily solved in the derivative form as they are using these notions of the Laplace variables. So typically in a circuit, when we see a capacitor, our interest really is its impedance, the ratio of the voltage to current at a given frequency determined by S equals J omega. Same thing with inductors. Often we're most interested in the impedance of the inductor. And of course, what we see in both these cases is the Laplace variable is the thing that determines the impedance. And so just kind of reviewing the big picture, what the role of Laplace transform is, and why it occurs in so many engineering problems. Inverse Laplace transform, again, I mentioned it's a contour integral in a complex plane. It has to be in the region of convergence, or the region where the x of s exists. Again, we use the frequency variable omega. It has the same units as always, so in radians per second. Later on, we're going to use the lowercase omega for digital frequencies, which have different units. So that's when we talk about Z transform. Typically, we don't do the contour integral, of course. We use for the inverse Laplace transform. The method we use is lookup tables, and we already have the lookup table. Often the form is not going to be convenient, and so you can do a partial fraction expansion to get it into the form that you find in the table, so that you break it into smaller pieces that appear in the table. And we'll see examples. So we already presented the lookup table, so just kind of quickly review partial fraction expansion. And so we'll just take the most simple case of first order pole partial fraction expansion. It's just more complicated if you have repeated poles, but you can review that in many textbooks and other resources, but just the basic principles we'll go over to here. So the first thing, when you have some Laplace function x of s, it has a numerator and a denominator. You need to have the degree of the numerator less than the degree of the denominator. If that is not true, you need to do long division to put it in the proper form until the remainder fraction has the form where the degree of the numerator is less than a degree of the denominator. So once you have that, you factor the denominator into its form where it has all the individual poles, and you still have the numerator. And so this must equal its partial fraction expansion. And so again, we're assuming single order poles. So each one of those poles is going to have a coefficient. And so on the right-hand side of the equation, it's going to be the sum of a bunch of terms of this general form of a numerator coefficient divided by the particular pole. And so again, we're assuming we have I different and unique poles from 1 to I for this denominator. Um, so to do the partial fraction expander, or see how it works, let's just take a look at this and multiply both sides of the equations by s minus one of those poles. Let's call it the kth pole, and see what happens on both sides of the equation. And so, at s equals one of the pole locations, the left side of the equation, we'll just leave the same for now. Again, substituting s equals a piece of k, we'll see cancellation with the kth pole and the leading term. But more importantly, on the right side of the equation, so only one of these terms at s equals p sub k, notice that we're multiplying by 0. And so the only term that's going to remain on this summation is the term that has the same pole location. And so the only thing that will be left on the right-hand side is c sub k. And so if you write that out, all the other terms will become 0 at the location of the pole. And so this is the formula that allows us to solve for each of the coefficients in a partial fraction expansion. So we need to find the c sub k's on the right-hand side to break it into its individual terms. So all we do is multiply the whole numerator and denominator by s minus p sub k to solve for c sub k, and also replace s by p sub k. And so once you do this for each, then you have the partial fraction expansion, since now you'll know all the constants in the numerator terms. So you have a sequence here on the right-hand side, a bunch of terms that look like c over s minus some pole location. And each one of these is going to have the basic form, right, of the Laplace transform. And so this will set the pole locations. So expanding this for the partial fraction expansion on the right-hand side, each term of the form 1 over s plus a will lead to a term that looks like c sub a e to the p sub a t. And so be careful of the sign differences here. We use the negative term in our definition for the partial fraction expansion, but the definition of the terms for the Laplace transform are different. So instead of e to the minus at for each of these, I have e to the plus, since I flipped the sign in the partial fraction expansion. So just be careful with that, and do the partial fraction expansion. So each term, so again, we're trying to find x of t. So each one of these terms on the right-hand side leads to e to the at u of t form. And now we know all the constants. And so this allows us to find the full partial fraction expansion. So I think it's easiest to just review this with an example. And so here we have s squared plus 1 over s plus 3, s plus 4. Because the numerator has the same degree as the denominator, that tells us we must do a partial fraction expansion, a long division first in our partial fraction expansion. So we just expand the denominator into all its terms and divide that into s squared plus 1 numerator. And so that goes one time. So that's our first term. And so then we subtract that from s squared plus 1, and we get a remainder of minus 7s minus 11. And so now x of s is rewritten as the 1, which was the term that was divided out, minus the remainder divided by the original denominator terms. And so then we can proceed to expand and solve for the coefficients. So again, the coefficient for the s plus 3 term is found by taking s plus 3 divide and using that. Oh, by the way, I'm doing the full expansion, so the 1 comes from out front here, so that doesn't change. And so I'm going to do the partial fraction expansion on the second piece. And so I need to do the partial fraction coefficient for the first term, which we chose to be s plus 3 on the bottom here. So I multiply out front by s plus 3. The s plus 3's will cancel. And I do the evaluation at s equals minus 3 for the pole location. And so I substitute minus 3 for s in all the terms that are there. So canceling these two terms gives me this final term here where I replace all the s's by minus 3. Same thing for the expansion of s for the s plus 4 term in the partial fraction expansion. So I multiply s plus 4 up front. That's going to cancel these two here. And then I'll have s minus 7s minus 11 over s plus 3. Again, since I was using the s plus 4, so the pole location's at minus 4, I do the substitution on that. And so once I have the cancellation of these two terms up front, that leaves me with this term here below that we replace the s's by minus 4. So once I replace the s's by minus 4, I get 10 over s plus 3 and minus 17 over s plus 4. So this is the partial fraction expansion. And so notice that these terms, of course, are in the form that you find in our Laplace transform table. Finally, completing the Laplace transform, each one of these leads to an e to the at, e to the minus at u of t kind of form. And so I have 10 e to the minus 3t u of t for the first one, and minus 17 e to the minus 4t u of t for the second term. Also, don't forget, we had a 1 up front. The inverse Laplace transform of a 1 is delta function. So we find, using this method, we find the solution for x of t. So as we mentioned earlier, Laplace poles are an indication of stability of a system. And so kind of the example, simple example we had earlier, 1 over s plus 4 for Laplace transform has a single pole in the s-plane at s equals minus 4. And so if we have the real axis and the imaginary axis, the pole locations to the left of the imaginary axis by 4. A system is bounded input, bounded output stable if all the poles are in the left half plane. And so that's to the left of the imaginary axis. And so this means that the region of convergence for these examples, we're doing one-sided Laplace poles, goes to the right. And so it includes the j omega axis, or the imaginary axis. Again, capital omega is what we're using for the continuous time frequency variable in radians per second. And so in this case, if we recall, the response was exponential decay, so e to the minus 4t u of t. So a well-behaved function is a function of time. And so this response, if you recall, is the type of response you have for an RC filter. So if we have an R and a C, its impedance is 1 over SC as a voltage divider, right? So if this is V in, this is V out. V out over V in would equal 1 over SC over R plus 1 over SC, and that equals 1 over 1 plus R, S times RC. And so that has the general form of the equation. So this has a single pole at a location minus 1 over RC for the RC filter. And so clearly an RC filter is a stable system. If h of s was 1 over s minus 4, the only thing changed is I have e to the plus 4t instead of e to the minus 4t. And of course, that would be a diverging exponential. And so it's clearly going to be an unstable system. This would be a pole location over here. And that would be a pole location that's not in the left half plane. Finally, we mentioned the examples when I had a pole at 0. That is not stable. That's the integrator. And we made the argument that if I have a step at the input of an integrator, the output is a ramp. And in that case, it diverges too. I have a bounded input, but the output is not bounded. And so one of the important features of Laplace transforms is to indicate stability of systems. We'll just kind of mention Fourier transform real quickly, quick review. Again, the Fourier transform of g of t is g of capital omega, again in our use, since we're going to talk about both digital and analog frequencies, we reserve the capital omega for our analog transforms. So instead of e to the minus st, of course, Fourier is e to the minus j omega t, and it's an integral minus infinity to infinity. That's the same as the Laplace transform, two-sided Laplace transform at s equals j omega. Just kind of mention that. For causal signals, by the way, the two-sided Laplace transform is the same as a one-sided, since it's 0 for all values less than 0, time equals 0. And the inverse Fourier transform 1 over 2 pi integral g of omega e to the plus j omega t d omega. So just a quick review of Fourier transforms. Some properties we may make use of. So the product of two functions is 1 over 2 pi the convolution of their frequency domains. And the convolution of two functions in time is the product of their two Fourier transforms. Some common Fourier transform pair, of course, the rectangular pulse gives a sinc function in frequency. By the way, the definition of the rectangular pulse, tau wide, is the pi or Greek capital pi or gate function, or pulse of t over tau would be a pulse tau wide, 1 high, centered at 0. Similarly, we define the triangle function tau wide, and so this is tau width, 1 height, and a width of tau. One last definition real quickly is the periodic impulse train, where the impulses are separated by t0. Again, these are infinitely high, but area 1. Or just write it out as the infinite sum of delayed versions of the impulse. So again, with this definition of the rectangular pulse, it's Fourier transform as a sinc function. Sometimes it's more convenient to write the sinc function using complex exponentials, just mentioned. Triangular function, its Fourier transform is a sinc squared function. Again, sinc function, I will use the more common definition, the sinc function sinc of x equals sine of x over x. Some authors include a factor of pi, but the sinc function, whenever you have a question on that in the Fourier transform table, you should be able to figure out what the definition of sinc is. E to the j omega t at frequency omega 0 gives a delta function in the frequency domain at frequency omega 0 with weight 2 pi. One last thing to mention here as I'm talking about this, we are doing the Fourier transform definition e to the j omega t. Another common form is j2 pi ft. You have to be very careful. The Fourier transforms have subtle differences. So for our purposes, our use, we're using the omega form rather than the frequency in hertz. Again, the infinite impulse train, its Fourier transform is an impulse train in frequency where the separation in frequencies is omega 0. Multiples of omega 0, so there are infinitely many in the frequency domain too, but they have a weight 2 pi over t0. Again, 2 pi over t0 is the definition of omega 0. And so, one last thing. The Fourier transform pair is the two-sided. Some texts use a one-sided impulse train. And so the definition I've given below here goes from minus infinity to infinity as sketched above, two-sided. So to the left of 0, I have impulses. So just a quick review of Fourier transform, which is related to the Laplace transform. So just kind of noting, Laplace can also be created from Fourier. So if you have a causal function, the Laplace transform of that function, right, is x of t e to the minus st. And we can break it into its two pieces. And we can see that this could be taken to be the Fourier transform of the first piece. And so we can use Fourier transform to find Laplace transforms just by multiplying the function by e to the minus sigma t and taking its Fourier transform.